Okay. I'll get this down at some point. Okay. Anyway, 300 grams of NH3, 1,000 grams of O2, find the limiting reagent, find the grams of everything present after the reaction. I'm going to tell you this is a very typical problem. This is kind of what I want you to be able to do in terms of chemical math. Okay, so we're going to work it the same way we did yesterday. And so what we do is we take our 300 grams of NH3, which was our starting amount of NH3. Fundamentally, the question we should be asking ourselves is, out of that, how much product can I get? Okay, kind of relating it back to the cars example. Okay, so from grams of NH3, you go to moles of NH3. And again, this is just kind of a function of the whiteboard. That's the only way I can put in a conversion factor like that. So it's 1 mole of NH3 over 17 grams of NH3. That gets us in terms of moles of NH3.
Uy, ¿tú tienes la calculadora?
Say that again. Did you have a question? I couldn't hear it.
Oh yeah, I was wondering the problem that you put like 17.64. Where do you get that? From where?
What? I don't know what you're talking about.
Like in the problem on the, yeah, that one, like 17.64, from where do you get it?
Sorry, this should be 17.64. Oh my goodness. Hang on. This should be 17.64.
Okay, I get it. Thank you.
Okay. Yeah, sorry about that. I hate this whiteboard. Anyway, so anyway, going through the calculation from grams of NH3, you go to moles of NH3. And then moles of NH3 go to moles of one of the products. Again, like we talked about yesterday, it doesn't matter which one. You just need to pick the same one both times. So for this example, I just did NO2. And essentially what this calculation is telling me then is what? From my 300 grams of NH3, I can possibly make 17.64 moles of NO2. Then I do the same thing for the given amount of oxygen, starting with 1,000 grams of O2. From grams of O2, go to moles of O2. And again, I apologize. I was kind of trying to get this on here at the last second because my other file wasn't coming through. But this from grams of O2 will convert us to moles of O2 from there. And then from moles of O2, you want to go to moles of product. Again, it's NO2 because we picked NO2 before. So you could have done the same thing for water. If you think about it, you get 6 waters for every 4 NO2s, or 1.5 times as much water for every NO2. So if you take this number times 1.5, this number times 1.5, this is still going to be the smaller amount. And that smaller amount tells us what? Anyone?
That's all you can use.
That's all you can make, right? Kind of going back to the cars example yesterday. Once you get here, the reaction's done. The reaction's done because what would you say about the NH3?
It's the limiting reagent.
It's the limiting reagent. It's all gone, right? So just like if you don't have any, I think we ran out of doors yesterday. I don't remember exactly. If you run out of doors, you can't make any cars. If you're out of NH3, your reaction's done. So based on comparing these two numbers, right? You look at this number compared to this number, and then you want to pick the smaller number. Look at that, I'm an expert at this thing. All right. Okay, you want to pick the smaller number because the smaller number tells you that thing's going to run out first. And when you run out of something, again, like I said, your reaction's done. So from that, we can essentially say two things. We would say NH3 is the limiting reagent. And we would say, since it's the limiting reagent, it runs out. We have 0 grams of it left at the end of the reaction. Okay. All right. Now, the important thing to remember is once you've done that calculation, You got the moles of NO2 there. You got the moles of NO2 there. All other calculations are based on this small number. So kind of what you should be asking yourself is, what do I know happened in this reaction? What I know happened in this reaction is this. I got 17.64 moles of NO2. That's 17.64 moles of NO2 starts my calculation for NO2, H2O, and O2. Okay, so I got 17.64 moles of NO2. Very simply convert that to grams of NO2. Okay, so moles of NO2 using the gram to mole conversion, you go to grams. I got 811.4 grams of NO2. Okay, and then like I said, I was kind of typing this in at the last second, so I kind of skipped a little bit here. But again, starting with 17.64 moles of NO2, from moles of NO2, if I'm interested in water, from moles of NO2, I would go to what?
Grams of the other product.
Eventually, but what would my first conversion be?
To
I think you were going to say it.
was it going to be moles of the other
Yes.
product?
Yes, so moles of NO2 to moles of H2O. And then once you have moles of H2O, you go to grams of H2O. So that would be similar to these up here. And again, you can look back at the example problem we did. Again, I apologize, just didn't get these in on time. My other file didn't upload. So from moles of NO2, you go to moles of H2O, moles of H2O to grams of H2O. Hopefully those conversions are trivial for you at this point. When you run through the math, you get 476.3 grams of H2O. Okay. Then NH3 ran out. We could have made 17.86 moles of NO2 from the given amount of 17.86 moles of NO2 from the given amount of O2. We only made 17.64, so we're going to have some O2 left. In other words, O2 is our excess reagent. Okay, so how much do we have left? Well, running through the numbers again, you're starting with 17.64 moles of NO2. From moles of NO2, go to moles of O2 using the mole to mole conversion factor based on the coefficients. Once I have moles of O2, I can go to, someone make my day,
Grams of O2.
grams of O2. And now do remember that this is a little bit different because O2 is a reactant that tells us what's happening to it as the reaction proceeds. What's it doing? It's going away.
Stop.
You guys aren't as good as you were the other day. Okay, we'll get better. I'll hope you'll get better. Okay, so it's a reactant. It's going away. So when you run through the calculation there, what's it telling you? It's telling you how much is used in the reaction. Okay, so from 17.64 moles of N2, you run through the calculation, you're going to get 987.8 grams of O2. Since we started with 1,000 grams, you used up that much. That means you have 12.2 grams of O2 left. Okay. Did we do this right?
Yeah.
How do we know? What can we do to verify?
Look at the ending amount.
Yep.
We would
add
add up the
Mass.
numbers.
We started with 300 and 1,000. We started with 1,300 grams of stuff. We better end with 1,300 grams of stuff, right? So you have 811.4 grams of this, 476.3 grams of this, 12.2 grams of this, 0 grams of this. Adding those up, we get 1299.9 grams at the end of the reaction. Is that good or bad?
It's good.
Good, right?
Yeah.
Because again, like I said, it's off a little bit due to rounding, but that's not a big deal. Okay. How'd you guys do on this problem?
Good.
Decent?
Yeah.
Good.
Okay, good.
I just messed up at the end of it.
Yeah, so is this, you said you had, I think you said you had 1288.
1288.
Is this what you
Something.
forgot?
I think so.
Yeah, that probably counts for that. So anyway, so there's another example of a limiting reagent problem. So you guys need to be working on these on Newton, hopefully. And I don't know if you saw the note from me, I did adjust all the dates and I did post your test dates. So I was ambitious as opposed to being overly cautious and said your test was going to be on April 7th. I just want you to be aware there is a possibility that will get moved to the 9th, depending on how fast we get through our material. But for right now, it'll be April 7th, which is 2 weeks from last Tuesday. Okay. Questions on this while this is up here? Before we go back into the notes?
What are you gonna, will you be posting grades on Blackboard now since we can't get any papers back physically?
I'm gonna defer that question. I mean, probably that's what I'm gonna do. I need to talk to one of you guys at some point to see what you can see. I don't know if you see your grade center. Obviously, you don't see everyone else's grade center. Is that right?
Yeah, we can't see everyone else's.
Okay,
Yeah,
'cause
no.
do you see the grade center? Obviously, there's nothing in it yet, but do you see like the columns for the grades?
I'm checking right now. I can. Oh, I don't even know if I can see our class in the grades until you post one.
Okay. You'll know your grades. I haven't figured out how I'm going to get you. I mean, Blackboard's kind of the obvious thing. That's better for me than sending out 70 emails. So likely that's what it's going to be. But I'm not 100% sure yet.
Okay, just correcting myself. I can see it, but there's
Okay.
nothing in there.
Okay, but nothing's in there, obviously.
Yeah.
Okay. All right. So, all right. Let me get out of this. I need to get into Blackboard. Okay. Let me just check here. I don't see any chat, and I think everyone's in here who wants to be in here. So hopefully this is calling up. Are you guys seeing my notes now?
Yep.
Okay. So going back to what we talked about yesterday, this was the same problem. Okay. So the next thing we're going to talk about is we need to talk about percent yield, because like I said, You don't always get what you think you should get because you can have different things going on. You might have some unreacted starting material. You might have some side reactions occurring, things like that. So typically, like we did for the copper lab, we calculated percent recovery because we were getting the same thing back. For a chemical reaction, you calculate what's known as percent yield, where we say that the percent yield is the actual yield, which is what you get, expressed as a percentage of the theoretical yield for a reaction. Okay. The actual yield is what it sounds like. It is actually the amount of product you obtained during your experiment. So again, tying that back to the copper lab, what'd you do? You ran through your stuff, and at the end of the reaction, you weighed out what you got, and that was your actual yield. Okay. Same thing when you do a chemical reaction, you would run through the experiment, isolate and weigh a product, and then that is your actual yield. Okay. So that, I like to say that that's experimental. You actually take it over the scale, weigh it, and see what you got. What you're doing is you're comparing that to the theoretical yield, where the theoretical yield is the maximum amount of product that you can get based on the given starting materials. So that's calculated, and that's actually the calculations we've been doing to this point, right? So kind of, let me creep back up here a little bit. Going back to our previous problem, sorry about switching back, but from the problem we did yesterday, we calculated we should have gotten 410.6 grams of NO2 based on our amounts of starting materials. So that would be the theoretical yield of NO2, just like the 241.0 grams of water would be the theoretical yield of water. Okay. So those are theoretical yields. Again, to get the actual yields, you would have to isolate those things chemically and then take them over the scale and weigh them. All right. Okay, so showing that kind of as a formula, your percent yield is your actual yield divided by your theoretical yield, and then multiply by that number by 100 to get a percent. So again, tying that into the problem we did yesterday. Again, going back to, here, showing you, we were supposed to get 410.6 grams of NO2 based on our initial amounts of stuff, okay? Taking into account what was the limiting reagent, and then how much are we supposed to get, okay? So basing our example off that, let's say we isolate and weigh 375.0 grams of NO2. Based on that, we want to find percent yield. So the 375 is my what? Actual or theoretical?
Actual.
Actual. And my theoretical is?
410.
10.6.
The 410.6, right? That we calculated, okay? So to set that up, this is pretty much a matter of just punching in and going. 375, your actual yield, divided by the 410.6 that you should have gotten based on initial amounts, multiply by 100 to get a percent, and you got 91.3% yield for that particular problem. Okay. Questions on that? We are going to, let me verify that we're going to. I believe what we're going to do, we're going to do one more limiting reagent problem, and we are going to incorporate theoretical yield into it. So any questions before we tackle that? Good to go for now? Let's give it a shot. Okay. Here, you might find this note to be useful. This type of problem will be on exam. Okay. I would say that's pretty good. Okay. All right. So that's what I want you to be able to do, right? and I will give you the balanced chemical equation. But think about generally what this problem is going to entail. Given a balanced equation, given amount of one starting material and amount of another starting material, I'm going to ask you, what's the limiting reagent? How many grams of each thing are left at the end? And what's the percent yield? Okay. So kind of how this is written out, what I did was kind of one of the first things you might want to do to help yourselves out is just get your molecular weights down. Okay, so C3H8 is 44, so 44 AMUs per molecule or 44 grams per mole. Oxygen's 32, CO2 is 44, H2O is 18. All right, so let's kind of talk ourselves through this. I'm gonna make things a little less visible. Okay. What do I do? How do I start? How do I find the limiting reagent?
You have to choose a product.
Yep. And
You have to find moles of that product using each gram measure.
yes. So
After we-
starting with my 145 grams of C3H8, fundamentally, the question I should be asking myself is what? How much product can I get from this process? Then do the same thing for the given amount of the other starting material. From 400 grams of O2, fundamentally, I should be asking myself, how much product can I get? Okay. You have two products to pick here. Doesn't matter which one you pick, but you do need to pick the same one both times. All right. So let's take a look at that. From my 145 grams of C3H8, what's my scheme? We said we wanted to know or relate that to product. So again, remember, for two chemicals to kind of talk to each other, if you want to think of it that way, they have to be in terms of moles, right? So from grams of C3H8, my scheme is to go from grams of C3H8 to moles of C3H8. And then moles of C3H8 to moles of product. Looks like I picked CO2 here. Doesn't matter, you could have picked water. We did CO2, so we're gonna do CO2. Okay, run through the calculation. What this calculation is telling me is from my 145.0 grams of C3H8, I could possibly make 9.89 moles of CO2. All right. Now what do I do?
Do the same with the oxygen.
Do the same thing for the oxygen, okay? So from the given amount of oxygen, 400 grams of oxygen, your scheme, you need to relate it to a product. And since we did CO2 here, we want to do CO2 here. So your scheme to get there is grams of O2 to moles of O2. Once you have moles of O2, go to moles of CO2 by using the mole ratio in the equation, okay? So running through that calculation, I got 7.5 moles of CO2. All right. Any question on where any of these came from or anything up to this point in the problem? Any questions?
So basically you're taking the 145 against the molecular weight, and then in order to cross both of those out, you have to put moles on the bottom again on the C3H8. And then you take that over the product that you picked.
Yes. So
That's it?
So, I hate to say it that way, but yeah, that's it. So,
Did I dumb it down too much?
well, I like to say a lot of times it's easy when I'm standing up at the board doing these problems, right? You're gonna know you know it when you do it yourself. So that's practicing problems or working the problem like I gave you last night.
Right.
But yeah, essentially, if you're trying to relate C3H8 to one of the products,
Mm-hmm.
you need to go into moles first because these coefficients allow them to be converted to in between or back and forth based on moles or
Right.
molecules, but usually that's not that useful for these.
And the molecular weight has to go on the bottom in order to cross it out and to go
Yes.
to moles. Okay.
So to go from grams to moles,
Yeah.
it's 1 mole over whatever the weight is.
Right.
That
Okay.
gets you in terms of moles. And then once you're in moles of one thing, you can go to moles of anything else in the equation. That or that or that. We want
Okay.
it to be a product, so you pick one of those two. And I just happened to pick CO2. It didn't matter if you picked water.
But pick the same one for the next one.
Right.
Okay.
Yep. Are we all good?
Yeah, I would say
Okay.
so.
Okay.
Mm.
So tell me what I know at this point. From my 145.0 grams of C3H8, I could possibly make 9.89 moles of CO2. From my 400 grams of O2, I could possibly make 7.5 moles of CO2. Someone tell me what happens.
The oxygen will run out, so you'll only be able to make 7.5 moles of.
Yep. Once you get to 7.5
products.
moles of CO2, your O2 is gone. If your O2 is gone, your reaction stops. In other words, O2 is our limiting reagent, and we will have none of it left at the end of the reaction. Okay. So continuing on, again, all your important numbers, look at the 7.5 moles of CO2. This number is irrelevant anymore. The CO2, 9.89 moles of CO2, you never get there. All your calculations, 7.5 moles of CO2, we bring that down, bring it down, bring it down, and then relate it to the other substances. So we got 7.5 moles of CO2. Very simply convert that to grams by using molecular weight. Okay, so that again, hopefully is becoming a trivial conversion factor for you. So in getting 7.5 moles of CO2, we will get 330 grams of CO2. In getting 7.5 moles of CO2, you use the mole ratio to figure out how many moles of water you get. And then from moles of water, convert to grams of water. And that's what I happen to get for that. Okay. And then from moles of CO2, related to moles of C3H8, remember moles of C3H8, C3H8 is a reactant, it's going away. Since we could have possibly made 9.89 moles of CO2, we know we're gonna have some left over because we only made 7.5 moles. Okay. So from moles of CO2, go to moles of C3H8, moles of C3H8 to grams of C3H8 using its weight. And what we calculate for that is I got 110 grams of C3H8. Now, remember this is a reactant, so it is a little bit different. This is going away. This number tells you how much went away. Okay, so we had started with 145.0 grams. 110 grams of it went away. So that leaves us with 35 grams left. Okay. And so what? What do we want to do?
We want to add all those numbers together.
Yep. Check your answer by conservation of mass. 35 plus 180 plus
330.
Plus 330 from there gives me 545 grams. We started with 545 grams. We ended with 545 grams. So that makes us happy. All right. I draw a smiley face on here, but I don't want to mess up the screen. All right. So Started with 545, ended with 545. That's good. That's what you want. Okay. So finally, percent yield. Going back to what we were told in the original problem. Find percent yield if 250.0 grams of CO2 is made or produced. Okay, so that 250 grams is our what? Actual or theoretical?
Actual.
Actual. Our theoretical was our calculated 330. Okay, so we're simply going to express those as a ratio. We got 250. We were supposed to get 330. Divide them out, multiply by 100 to get convert to a percent, and you get 75.8% yield.
How did you get the 250 again?
That would have just been given in the problem.
Okay.
Okay.
Oh, I see it now.
Yeah. Okay. Can you guys do that?
I think I can do it. I mean, I hope
Okay.
I can.
Well, I'm going to find out eventually if you can do it. Okay. So practice these on Newton and things like that. You guys, the nice thing about these problems, you literally can make up an infinite number of these problems. Start with a balanced equation, make up gram amounts of materials, and what should happen is in the end, you should end up with what you started with. Okay. So there's no limit to the number of these problems you can do. Okay. Looks like we're going to solutions. So let me one more time. Any questions on this? Okay, for my own satisfaction, I'm going to say we're going to run through this one more time real quick. I'm going to talk you through this thing. Here's a balanced equation. Given an amount of each starting material, you need to be able to say what's the limiting reagent, how many grams of each thing are left at the end. Okay. So from the given amount of C3H8, the question you should be asking yourself is how much product do I get from that process? Okay. Grams of reactant to moles of reactant to moles of product. You got your number there. Then do the same thing for the other one. Grams of reactant to moles of reactant to moles of product. Again, like we said, you've got to pick the same product for both calculations. It doesn't matter which one. Compare. Whichever one produces the least amount of product is what's going to kind of govern that reaction, because once you get that much, you're going to run out of whatever reactant gave you that, and your reaction is going to stop. Okay, so all your other numbers are based on this. Again, that I would call that another key. You never get to 9.89 moles. You only get to 7.5. So 7.5 moles starts all of your other calculations. Okay, so for moles of CO2, go to grams of CO2. For moles of CO2 related to the moles and then the grams of the other substances in the reaction. So moles to grams got us our water. Moles to grams got us our grams of C3H8, which was reactant, so it's going away. And so take the amount you started with, subtract the amount you used, gives you the amount left. Like I said, the nice thing about these problems is you can add them up. You start with 545 grams, you end with 545, so that's good. Okay. So again, being able to verify your work is a handy thing to do. All right. Any questions? Last chance. Okay. Next thing we're going to do then is we're going to talk about solutions. We've already done a little bit of this in lab. And for those of you who have lab on Wednesday, the titration lab involves dealing with solutions. Okay. So just I'm going to kind of skip over some of this pretty fast, the definition stuff. You guys can go back to it. But we can define a solution to be a homogeneous mixture of two or more substances consisting of ions or molecules. Those solutions can be solid, liquid, or gas. The solute is the stuff that is dissolved. The solvent is the stuff that it's dissolved in. Okay. So, like I said, it is possible to have gas solutions. A very good example of a gas solution is air. Okay. It's possible to have solid solutions. A good example of a solid solution is brass, steel. Now, to make them homogeneous, they need to be melted first and then solidified. Okay. But normally when we think of solutions, what do we think of?
Liquids.
Liquid solutions. And even more typical than that, we think of what? Stuff dissolved in water, right? Salt water, sugar water, stuff like that. Okay. Now, to make a liquid solution, first of all, it's got to be soluble. We need to be able to dissolve it. Okay. So you can't make a solution of glass and water. Glass doesn't dissolve. Can't make a solution of sand and water. Sand doesn't dissolve. But you can make a solution of salt and water or sugar and water. And so that the thing we're going to talk about next is solubility. Solubility kind of defines the limits of how much of that given substance you can get to dissolve. Okay, so we can define solubility to be the amount of solute that will dissolve in a given amount of solvent at a given temperature to give a saturated solution. Okay, so a saturated solution means no more can dissolve. And just to give you an example of that, and this is very typically how solubility should be stated. For sodium chloride, the solubility is 36 grams per 100 milliliters of water at 20 degrees Celsius. Okay. Because we do know, just from everyday experiences, solubility is temperature dependent, right? Typically, you can get more stuff to dissolve in a hot solution than you can in a cold solution. Okay, thinking of sugar or whatever. All right. Now, if I can get 36 grams of sodium chloride to dissolve per 100 milliliters at 20 degrees Celsius, I can also do what? Have a solution that has 1 gram or 2 grams or 3 grams or 4.976 grams. So another important characteristic of solutions is concentration. Okay. How much solute is there for how much solvent? All right. So one way of expressing concentrations, probably the most common way of expressing concentrations in terms of everyday life kind of things you run into, is percent. And a good example is if you have a 5% sugar solution, what does that mean? You would have 5 grams of sugar and 95 grams of water. So 100 grams total. 5 out of those 100 grams are sugar. So 5 out of 100 times 100 to convert to a percent would be a 5% sugar solution. Okay. Another way of expressing concentration is in terms of molarity. And again, if you've done the buffers lab, we talked about this a little bit. We may have also talked about it a little bit with the copper lab. Molarity is defined to be moles of solute over liters of solution. Okay, so like in the lab, when you see a bottle of stuff, if it's something in aqueous solution, for example, 3.00 molar sodium hydroxide, what that means is there are 3 moles of sodium hydroxide per 1 liter. Okay, so it's a ratio of amount of solute per amount of solution. Okay, Now, what we can do with this, we're going to have another important conversion factor pop out of this. What we can do is we can go from moles of something to liters of something, or from liters of something back to moles of something. Okay? Because you can use this as a conversion factor. It tells us how many moles we have per liter or how many liters we have per mole, because you can do the reciprocal of this conversion factor, which we get from the fundamental definition of molarity. All right. So like it says, if I have 20 milliliters of 3 molar sodium hydroxide, how many moles are there? Okay. So what I want you to do in terms of these problems is think about it. Molarity is moles per liter. If I take moles per liter and multiply by volume in liters, I'm going to get moles. Okay. So think of molarity as a conversion factor. Again, it allows you to go from moles to liters or liters to moles. If I have my volume in liters and my molarity, I can get moles. Okay. So one of the things that's going to be helpful to you guys is if I tell you you have 20 milliliters, you need to be able to kind of quickly tell me how many liters that is. So what do you want to do? 1, 2, 3. Move your decimal 3 places. 20 milliliters is 0.0200 liters. Okay. All right. So I have 0.0200 liters. My concentration is 3 moles per 1 liter. So in my solution, I have 0.0600 moles of NaOH. Okay. So in 20 milliliters of 3 molar NaOH, there are 0.06 moles of NaOH. All right. Now, once I have moles of NaOH, I can go wherever from there, right? We can go from moles of one thing to moles of another thing, or you can do pretty much anything once you have things in terms of moles. Okay. Anyway, I think what I was doing there was I was introducing this to them because we were running into it in lab. So I think I talked about that in lab with you guys a little bit, or talked about it on Monday for Monday's lab. Talked about that with you then, and for Wednesday's lab, hopefully before we went on spring break, that got introduced a little bit to help you out with some of those problems. Okay. Going back to solubility, if you think about the maximum amount of stuff that can be dissolved, you're going to have 3 types of solutions. You can have a saturated solution, and a saturated solution contains the maximum amount of chemical that it can, and that is based on solubility. Okay. If you have less than that maximum amount, you have an unsaturated solution, so more could possibly dissolve. Okay. And it's also possible to have what's known as a supersaturated solution, and those supersaturated solutions actually have more solute than it supposedly can at a given temperature. And that kind of comes about because of the fact that solubility is temperature dependent. So usually you'll change temperature to get a supersaturated solution. Okay. All right. So what we know, remember we were given the solubility of sodium chloride earlier. Solubility was 36 grams in 100 milliliters of water at 20 degrees Celsius. So here's a sample problem. Using our definitions, if we have 10 grams of sodium chloride in 35 milliliters of water at 20 degrees Celsius, we want to know, is it saturated, unsaturated, or supersaturated? Okay. So there's a couple different ways of solving this problem. What I like to do is I like to say, okay, I have 35 milliliters of water. What do I know? I know 36 grams of water 36 grams of sodium chloride can be contained for every 100 milliliters of water. So you can use that ratio as a conversion factor. If 36 grams can be dissolved for every 100 milliliters, 35 milliliters is going to be able to hold what? You can multiply that by a conversion factor. The other way to kind of set this up is you could set it up as a ratio. 36 over 100 equals X over 35. Doesn't matter how you do it. Mathematically, what you get is you get 12.6 grams. Okay. So what does that 12.6 grams tell me? That is what? Anyone? That's how much could dissolve in my 35 milliliters. Okay. Based on 36 per 100, which is my solubility. Again, that would be given to you. You don't have to remember that or anything. Okay. But based on this, my ratio for a saturated solution, my 35 milliliters could possibly hold 12.6 grams of sodium chloride. What is it doing? Is it holding that, holding more than that, or holding less than that?
Holding less.
Holding less, which makes it what?
Unsaturated.
Unsaturated. Okay. So that just goes back to what was given in the problem. Our 35 milliliters could hold 12.6 grams. It's only holding 10. So that's less than the 12.6 that it could hold. So it's unsaturated. If I had 12.6 here, it would be saturated. If I had 13.1 there, it would be supersaturated. Okay, so kind of comparing the amount you get there to the amount you were given tells you what kind of solution you have.
Why did they use grams? I know that he was given the grams of NaCl. Why didn't he or she, whoever did these notes, convert it into moles so it would be moles over liters?
Because then you would have to convert this to moles. I mean, you
So
have
you
to compare grams to grams or moles to moles, right?
Yeah.
So molarity really doesn't apply for this type of problem. Like I said, I kind of jumped to molarity probably to get out some information in lab or something, and then we kind of came back to this. So this is a little bit easier than dealing with molarity at this point. Does that make sense?
Well, we were given the conversion factor moles over liters. So
right. Look. So kind of going back here, I'm going to tell you that I went through this concentration stuff just to get some information out the lab. We're going to come back to this.
Okay.
Okay. This is more based on this idea of solubility.
All right.
Okay. So again, I probably gave them this just as an introduction to kind of plow through some lab problems. Okay. That will come back. That'll be important, but it's not important for this.
Okay.
Okay. The other thing you can get for solubility, again, for sodium chloride, our solubility is 36 grams per 100 milliliters at 20 degrees Celsius. I'm not always going to have 100 milliliters. In this case, I had 35 milliliters. The other thing you can use it for is you can say how many grams of sodium chloride would dissolve in not 100 milliliters of water, but 550 milliliters of water. Okay. So again, you're going to use your solubility as a ratio. I have 550 milliliters. I know 36 grams dissolves per 100 milliliters. So multiplying that out for my 550 milliliters, I get 198 grams could dissolve in my 550 milliliters. And that 198 grams of sodium chloride, if you got 198 grams of sodium chloride to dissolve in your 550 milliliters of water, what would you tell me about that? What kind of solution is it? Saturated, unsaturated, or supersaturated? Saturated. Okay, based on this, it's solubility, right? Its solubility always corresponds to a saturated solution. Okay. So the 550 could hold a maximum of 198. Now it could hold 100, it could hold 75, it could hold 0.1, it can hold whatever it wants up to that 198. Okay. All right. Now we're coming back to molarity. Okay. So like I said, kind of going back to this, it can hold up to 198. It can hold any amount up to that amount. So one of the important characteristics of the solution is how concentrated is it? Okay. And we introduced earlier, we can express concentration in terms of a percent. That's one way. Mostly in chemistry, we're going to use molarity, where again, molarity tells you moles per liter. So for example, if you were using a solution in lab, you would see it labeled very similar to this, 1.25 m HCl. What does that mean? It means there's 1.25 moles of HCl for every 1 liter of solution. So it is a ratio. Okay. All right. So one of the things we want to be able to do is we want to be able to make up solutions. Okay. So to make solutions, like it says here, given solid calcium chloride, CaCl2, and water, describe how to prepare 500 milliliters of 0.75 molar CaCl2 solution. Okay. So thinking about this problem, what's going to be in my solution when I'm done? Am I going to have sugar in my solution? Come on, you guys. I need you. Will I have sugar in my solution?
I think there was a connection issue. We didn't hear you for a few seconds.
Okay. So what is going to be in my solution?
See,
Oh, CaCl2 and H2O.
CaCl2 and H2O. Okay, so to make the solution that I want, what do I need to figure out? I need to figure out how much of this am I going to have, and how much of this am I going to have. Okay. So 500 milliliters of 0.75 molar CaCl2. Remember what 0.75 molar CaCl2 means. It means you have 0.75 moles of CaCl2 per 1 liter. Okay. So first of all, do I have 1 liter?
no.
No,
Yeah.
I have 500 milliliters. 500 milliliters is what?
0.500.
0.5 liters.
0.5 liters. Okay. So again, this is key, using molarity as a conversion factor. If I know molarity, moles per liter, if I multiply that volume by liters, liters times moles per liter gives me moles. Once I have moles of stuff, I can go to pretty much anything. Okay. So taking 0.5 moles times 0.75 moles per 1 liter is going to get me to what? What will my units be after that conversion?
Moles of CaCl2.
Moles of CaCl2. Okay. Now, I'm not going to weigh out moles of CaCl2 on the scale. So I want to figure out how many grams that is to know how much to weigh out. So I'm going to go from moles of CaCl2 to grams of CaCl2. And so that's its molecular weight. And so what I calculate is I need 41.6 grams of CaCl2 to make that solution. Okay, so that's how much CaCl2 is in there. All right. So to do that, to make your solution, what you're going to do is you're going to take 41.6 grams of CaCl2 and you're going to add water until you get to a total final volume of 500 milliliters. Okay. Now, one thing I want to point out to you guys, and this is going to be a little bit difficult to see. I'm going to try and draw this on the whiteboard as best I can. After I explain it to you, we'll see how it goes. You need 41.6 grams of CaCl2. Your total volume of solution has to be 500 milliliters. Okay, so you don't add in 500 milliliters of water because when you make solutions, it's possible, depending on what you're doing, solutions can expand or solutions can contract. So you don't add in 500 milliliters of water, you add in water until you get a total final volume of 500 milliliters. All right, so again, I'm going to go to the whiteboard and I'm going to draw as best I can, which already isn't great. It's going to be even worse on this, but I'll do what I can. Okay, and get a new page. All right. So we have these pieces of glassware called volumetric flasks. Okay, those volumetric flasks have one volume. Okay, so they really only have one calibration mark on it. So one example is I can have a 500 milliliter volumetric flask. Okay. That's chemical glassware that's not meant to smoke anything. All right, so we got one volume. It's got one calibration mark on it. So typically what we would do is we would put our 41.6 grams of calcium chloride on the bottom there, add in water to about 2/3 of the way up the neck, get it to dissolve, right? Because we want it homogeneous, then fill up to that mark, and then mix up that volumetric flask to get it to dissolve. There are stoppers that go on the top of this thing. So usually what you do is you invert this thing and then mix that up real well to make sure your solution's homogeneous, because you want the same concentration here as you have here as you have here. Okay. All right. So literally how you're going to describe that thing. Let's get off that thing. Literally how you're going to describe making that thing is you want to take 41.6 grams of CaCl2, and then you're going to add water until you get to 500 milliliters total of solution. Probably the best way to measure that thing or make that solution is in one of those volumetric flasks. Okay. So you should be able to describe how to make a solution like that. How are we making that solution? We're making that solution from a solid and water. Okay. What's another way we want to be able to make a solution? For those of you who did the titration lab, you've already seen this. Okay, and we talked about this the other day. For those of you who have lab on Wednesday, we talked about this dilution equation. The other possibility is what? Instead of a solid in water, you might use a high concentration solution and additional water. And if I start with a higher concentration of solution than I want and I add some water to it, what am I doing to it?
You're diluting it?
You're diluting it, okay? You're spreading out those molecules, lowering the concentration. Okay, so in the next problem, what do we want to do? We want to be able to describe a solution. In this case, we're not given solid. To make our solution, we're given 5 molar NaOH, and we want to prepare 250 milliliters of 0.200 molar NaOH. Okay, so we got to figure out how to do that. To do that, we're going to use something called the dilution equation. So for those of you who have lab on Monday, this is coming up. You're going to need this for your titration lab. And that the dilution equation essentially says the molarity of one solution times the volume of that solution is equal to the molarity of the new solution times the volume of the new solution. Okay. This assumes what's happening is dilution. In dilution, what you're doing is you're only adding in additional solvent, typically water. All right. So, looking at our problem here, kind of thinking about what this would look like. We have a bottle of 5 molar sodium hydroxide. That's our only source of sodium hydroxide. We want to make 250 milliliters of 0.2 molar sodium hydroxide. So we need to figure out, we got two things going in this solution. We've got our 5 molar sodium hydroxide and we've got water. Okay. Now, so simply punching in, and it doesn't matter what you call M1 and V1 or M2 and V2 as long as you keep them together. What we want is we want 250 milliliters of 0.2 molar NaOH. So M1 I'm going to say is 0.2. V1 I'm going to say is 250 milliliters. M2 is 500 milliliters. V2 is what we're solving for. Okay. Now, one thing to point out here is a lot of times you need to do what? If you're working with molarity, you need to convert your volume to liters. That doesn't need to be done in this case because whatever volume unit you have here is going to be your volume unit over there. So you don't have to convert to liters. You certainly could if you wanted to, but you don't have to. All right. So what do we do here? We crunch our numbers. So again, our setup is 0.2 times 250 equals 5 times V2. Okay, so I kind of went through the algebra here. Hopefully you guys are comfortable with this. Basically multiply those two, divide by the 5, and we solve and we get V2 equals 10 milliliters. So what does that mean? What that means is you need 10 milliliters of your 5 molar NaOH, and then the rest is water. Okay, so to prepare that, what you do is you take 10 milliliters of 5 molar NaOH and then add in 240 milliliters of water to get a total final volume of 250 milliliters. Okay. At least that's how we're going to do things. What I do want to point out to you, in this class, what we're going to do is we are going to assume volumes are additive. What do I mean by that? What I mean is if you take, go back to my whiteboard here and get to my lovely drawing. Let's go ahead and use a new page. If you take 100 milliliters of one thing, and then you take 100 milliliters of something else, does that equal, question, 200 milliliters? And the answer is no, it does not. Not necessarily anyway. Okay. Doesn't necessarily equal 200 milliliters. Again, like I said, you can have expansion or contraction of solutions when you mix them together. That said, we will, for our purposes, assume that they are additive. Okay, but I do want you to understand that they are not necessarily additive. Okay, so 100 mils of one thing plus 100 mils of another may or may not get you 200 milliliters. Now, it's not going to get you 300 milliliters. It's not going to get you 20 milliliters. It might get you 198.5. It might get you 204.1 or something like that. It's going to be close. So for our purposes, we're going to say it's close enough. Okay. Questions on that? Any questions on that?
Yeah.
Holy cow. I'm going to call that a good stopping point for today. And we'll pick that up on Tuesday. Okay. And we'll leave it at that. Okay. So kind of based on how far we got today, I'm leaning a little more towards 75% chance our test might be on Thursday the 9th. If that's going to cause problems, what we'll do is we'll go as far as we get, and we'll just have a test on the 7th. Okay. But be aware that the test might be on the 9th. If that's going to cause issues, we'll just stop where we are and we'll test on what we've covered on the 9th. Okay. I'm sorry, on the 7th, which is what it's scheduled for right now. Okay. Any questions?
This is terrible.
I
I know.
I'd like to
said it.
disagree with you.
I feel
cannot.
better that I just said it.
Yep.
I have a question.
Yes, go ahead.
So I know we have all the notes and everything basically, but you know how you usually give us like a study guide of everything we need to study? Are we gonna be given that too?
So I would say your notes are your study guide. My intention is to have a review before the test, like I like to do. I don't know if that will be in class during a lab meeting or if I'll have to set up something outside.
Okay.
Um,
And also, since like basically the science lab, I don't know if they're open through Zoom or anything, but is there any help we can get outside of you when you're busy or anything like that?
say that again.
So like I used to go to the science lab to get help with my chemistry homework and stuff like that. And when I was
Yes.
studying, do you know if there's anyone doing stuff like that?
So I did post some links. There are a lot of places that are doing like free things because this disaster is everywhere. Academic Skills is also available for tutoring. I will post that link on our Blackboard site. The other thing is I'm going to have office hours to help you guys. I thought about doing it tomorrow, and I'm not doing that to myself. I'm more done than you guys are. Okay, I will have some office hours for you starting next week. Okay, and so if you have suggestions, kind of what I'm thinking about doing is doing like a half hour every day, and then if there's demand for it, then I will increase that. If there's not demand for it, I may decrease it. But communication is key. Like I said, if you guys have questions, you need to email me, or you can kind of ask at the beginning or end of class specific questions. Like I know we didn't allot any time. Hey, do you have any Newton questions? So that is better served as office hours. Like I said, Academic Skills is available. I will get something out to you guys. Let me make myself a note about that.
And you also said all the other links are already on Blackboard.
There's some, I'm going to call them like help links and stuff. So they'll have links to PowerPoint presentations over dilutions of solution from like 15 different sources. Now, I'm not going to say they're all good. This list was provided to me. And I haven't checked every single one of them out individually. Some might be more helpful. I would give a little plug for Alex That is ALEKS. There's also Chem 101. Literally what you can do is Google help on dilution of solutions. Okay. And then from there, you can kind of figure out, okay, this is useful, this is useless. And take it from there. Okay. So there is help out there. Like I have told you guys, I am going to be as available as possible to you guys because I know this is not easy for any of us. This is not my wish either. Okay. But it is what it is. And frankly, I think we're coping with it reasonably well. Maybe we're putting on a good face, but I think we're coping with it reasonably well. Okay. So I'm going to leave it at that. Any questions? Okay. We'll call it good then for today. And